Hello! In this video I'm going to be talking about some of the rules for finding derivatives. Now in a previous video I introduced the idea of derivatives and I talked about how they're defined, what they represent, why we care about them, and I showed a couple examples of finding specific derivatives of particular functions directly from the definition, which involved evaluating a couple of reasonably complicated limits. But I mentioned that there was an easier way of finding derivatives, and that is to use some derivative rules where if you just follow what the rule tells you, you can sort of jump directly to what the derivative is, that is, to what that definition would give you if you did work through all the details without having to actually mess around with those details. So that's what I'm going to be talking about starting in this video. I'm not going to show you all the rules in this video, but I'm going to start with a few of the simpler ones. And these rules are presented in any calculus textbook as theorems, which means they can be proved. And so for at least some of them, I am going to be showing you the proof of the rule. So going back to the definition, we can work out exactly why that definition says that the rule has to work the way it does. Now, some people care about this, and some people don't. Some people really like the aspect of mathematics that is the logical structure, where you start with a few basic definitions and assumptions, and then building on that, you prove everything in terms of what you already know, so that you can be sure about everything that you've based on those initial assumptions. So if you don't care about that, you can safely ignore or skip the parts of this video that have the yellow border. But I am going to try to make them as simple and enlightening as possible. But to understand the proofs, you will have to understand the definition of the derivative that I presented in that previous video. Like I said, some people care about that and some people don't. Kind of like with cars or airplanes or computers, some people care about how they work and other people just care about using them to get where they want to go. Now, even if you don't care about the formal proofs, you might want to know, why does the rule make sense? On an intuitive or informal level, why does the rule work the way it does? Why does the rule say to do this instead of something else? Why is this the rule instead of something else that might seem like it ought to be what the rule should be? So, where possible, I'm going to try to say something about why the rule works the way it does. And based on the fact that the derivative of a function represents the rate of change of that function, and it also represents the slope of the tangent line to the graph of the function. So when I talk about why the rule makes sense, that's going to be the part of the video that has an orange border. If what I say helps you, great. If you don't find it helpful, you can just ignore it. And then I am going to be focusing a lot on how the rule works, how each rule is used to actually find derivatives of specific functions. I'll be working through examples that show you how the rule works in practice so that you can use it to find derivatives of your own functions. So that's going to be all about, given some particular function f of x, what is the derivative of that function? What is f prime of x? So here we go. First rule, the constant rule. The derivative of a constant is 0. So here c stands for any constant, any particular number. Not a variable, just a specific number. So this says that the derivative with respect to x of c is 0. Another way to put it is if f of x is c, so no matter what x is, you always get the same number c out of that function, then f prime of x equals 0. So for example, if f of x is 2, that is, this is the function where no matter what you put in for x, you always get 2 out as the output, the value of f of x. Then f prime of x would be 0. What about if f of x is negative 37.5? Then f prime of x is still 0. Not a very interesting rule and not all that impressive by itself, but it's going to be an important tool once we get all of our rules. This one, together with all the others, is going to be useful in finding derivatives of things that aren't just constant functions. To prove this, let's go to the definition. By definition, the derivative of any function is the limit as delta x approaches 0 of that function evaluated at x plus delta x minus that function just of x all over delta x. So in this case, if the function f of x is c, that means f of anything is c. F of x plus delta x is c, and f of x is c, and so we got c minus c over delta x. But c minus c, any number minus itself, is just 0. So we're looking at 0 divided by delta x. And remember, delta x isn't equal to 0, it's just approaching 0. It's close to 0. But on top we have 0, and then we're dividing by some other number that's only close to 0, so that always comes out to be 0. 0 divided by any other number is 0. And then the limit of 0, as delta x approaches 0, is 0. So that concludes the proof, that if f of x is c, f prime of x, the derivative is 0. And why this makes sense, intuitively, the derivative represents the rate of change of a function, but a constant function isn't changing. It always gives you the exact same value. So the rate of change of that function makes sense that that would be 0. And if you think of derivatives in terms of the slope, well, a constant function has a graph that is a horizontal line. It just goes right straight across. Like if f of x is the constant function 2, then every point on that graph has a y-coordinate of 2. So at every point on the graph, the slope is 0, because a horizontal line has a slope of 0. Another really simple rule is that the derivative with respect to x of x itself is 1. In other words, if f of x is the identity function, the function where whatever you put in for x, you always get out that exact same x, then f prime of x is the constant function 1. So to prove this, f of x plus delta x would be x plus delta x. You just replace the x with x plus delta x. F of x is x. So we're looking at the limit as delta x approaches 0 of x plus delta x minus x over delta x. But that numerator can be simplified. We got an x plus a delta x minus an x, and this x minus this x add up to 0 or cancel out. So the numerator simplifies to delta x. But now we're looking at delta x over delta x. Any number, and remember delta x isn't equal to 0, it's just close to 0. So any number, even one that's close to 0, divided by that exact same number always gives you 1. And now the limit of a constant is just that constant. So as delta x approaches 0, the limit is just 1. Why does this make sense? Well, again, the derivative represents the rate of change of a function. If f of x is just x, that is, what comes out is exactly the same as what goes in, then f of x is always changing exactly 1 times as fast as x is changing. And if you look at the graph of this function, at any point along this graph, well, it's just a straight line with a slope of 1. Now we come to a lot more interesting rule, the power rule. If n is any real number, then the derivative with respect to x of x to the nth power is n times x to the n minus 1 power. So if f of x is x to any particular power, the derivative f prime of x would be that original power times x to that power minus 1. Now I've written it with the letter n standing for the power, and you may be used to n standing for a whole number or an integer. And this rule is sometimes presented where the power is a whole number or an integer. And it's a lot easier to prove this if you just focus on what happens when you have x to a whole number power. But in fact, the same rule applies no matter what kind of number that power is. So it's still true if you have x to a negative power or a fractional power or an irrational power. It just gets harder to prove that. But the rule applies no matter what kind of number that power is, as long as it's a constant. So let me go ahead and show you some examples of this rule in action so you can see how it works. If f of x equals x cubed, that is, the function we want the derivative of is x to the third power, then f prime of x would be 3 times x to the 2 power. It's the original power times x to that power minus 1. What about if f of x is x to the 17th power? Can you see what the derivative of that ought to be? Well, yeah, it would be 17 times x to the 16th power. What about if f of x is x squared? Then the derivative would be 2 times x to the 1 power. And of course, x to the first power would just be plain old x itself. So it would make more sense to just write that as 2x. What about if f of x is x? Now we already know what the derivative of that is, but we could use the power rule on this because we could think of x by itself as being x to the 1 power. So now using this rule, with the part of n being played by the number 1, we get that the derivative is 1 times x to the 0 power. But any number to the 0 power is just 1. That's how exponents work. So this would just be 1 times 1, or 1. So really, we didn't need a separate rule that told us that the derivative of x is 1. We could just consider that as a special case of this power rule. Now, what about if f of x is 1? That's a constant function. We already know what the derivative of a constant function is. But suppose we think of this as x to the 0 power. And we apply the power rule to it. The derivative of x to the 0 power ought to be 0 times x to the 0 minus 1, or negative 1 power. But 0 times anything is 0. So that agrees with what we said before. And sometimes in math, there's more than one way of doing something. There's more than one rule that would apply to the same situation. So you ought to get equivalent results no matter which rule you use, as long as both rules actually do apply to your situation. So that gives us reassurance that what we're doing is correct and consistent. Now, what about if f of x is x to the 8.2 power? Remember, I did say that the rule applies even if the power isn't a whole number. So here the n is the number 8.2. So of course, n minus 1 would be 7.2. So the derivative would be 8.2 times x to the 7.2 power. What about if f of x is x to the negative 9 power? What's the derivative? Negative 9 times x to the negative 9 minus 1, which would be negative 10 power. What about if f of x is the square root of x? Now remember, another way of writing the square root of x is x to the 1/2 power. The cube root would be to the 1/3 power, the fourth root would be to the 1/4 power, and so on. So we can write roots or radicals using fractional exponents like that, and that means we can find the derivative using our friend the power rule. So if f of x is x to the 1/2 power, then the power rule says that f prime of x, the derivative, should be the power 1/2 times x to the power minus 1. And 1/2 minus 1, that would be 1/2 minus 2/2, so that would be negative 1/2. So for the derivative, we got 1/2 times x to the negative 1/2. And remember, a negative power is equivalent to a positive power in the denominator. So we could also write this as 1/2 times 1 over x to the positive 1/2 power, or 1 over 2 times the square root of x, because again, x to the 1/2 power is equivalent to the square root of x. So we've just seen, with the help of the power rule, that the derivative of the function square root of x is 1 over 2 times the square root of x. What about if f of x is 1 over x to the 4th power? Another way to write that would be as x to the negative 4 power. X to a negative power is equivalent to 1 over, or the reciprocal of, x to a positive power. So we can use the power rule with the part of n being played by negative 4. And we get that the derivative is negative 4 times x to the negative 5 power, which could also be written as negative 4 over x to the positive 5 power. Now, let me give you a warning here against something that I sometimes see calculus students do. Sometimes people will be working through their derivative finding problems, and they'll write something like this. This equals this, equals this, equals this. They'll just put equal signs on each line of their work, even if the things from one line to the next aren't really equal to one another. Now here, x to the negative 4 is equal to f of x, but it's not equal to negative 4 times x to the negative 5th. This is the derivative of this. So I want to be careful and specify that so that I don't confuse myself or anybody else who might be looking at my work. I want to be sure and say, well, this is f of x, and then starting here, this is something different. This is f prime of x. So f prime of x is a different function from f of x. It's related, but it is a different function. Just like if you have children, your son or your daughter is related to you, but they are a different person from you. The derivative of a function is related to that function, but it is a different function. Now, what about the proof of this? It's tricky to prove in general if we think of n as standing for any real number. But if I think of n as standing for the specific number 2, well, if n is 0, we already know that the derivative of x to the 0 power is the derivative of a constant, so that's 0. And we already know that the derivative of x to the 1 power, that is of x itself, is 1. So we've already seen that the rule works in those two cases. In the case where the power is 2, then the function we're looking at is x squared, and we would need to prove that the derivative of that function is 2x. So, using our definition, in the case where f of x is x squared, that would mean that f of x plus delta x would be x plus delta x squared. So the derivative, by definition, would be the limit as delta x approaches 0 of x plus delta x squared minus x squared all over delta x. Now, if you take that x plus delta x squared and multiply it out, remember what happens when you square a binomial. You take a binomial times itself, You get the first term plus squared plus 2 times the first term times the second term plus the second term squared. So here that's x squared plus 2x delta x plus delta x squared, and then minus x squared. But of course, this x squared minus this x squared cancel each other out. They add up to 0. So now we just have the limit of 2x delta x plus delta x squared all over delta x. Now, if we just went ahead and let delta x go to 0 now, we would have a numerator and a denominator that were both approaching 0. But we're not quite ready to let delta x go to 0. Instead, we're going to just take everything on top and divide through by the delta x on the bottom. So 2x delta x divided by delta x is 2x, plus delta x squared, which of course means delta x times delta x. If you divide that by delta x, you still have delta x remaining. And now we can go ahead and let delta x go to 0. So the limit of 2x plus delta x as delta x approaches 0 is 2x plus 0, or just 2x. So that completes the case that if f of x is x squared, the derivative is 2x. What about if f of x is x cubed? What if the power is the third power? Then the derivative would be x plus delta x cubed minus x cubed over delta x, and then the limit of that as delta x approaches 0. And if you take x plus delta x cubed and multiply that out, you get x cubed plus 3 times x squared times delta x plus 3 times x times delta x squared plus delta x cubed. And then we still have minus x cubed. So this x cubed minus this x cubed cancel each other out. And here's what's left. 3x squared delta x plus 3x delta x squared plus delta x cubed. And we're going to divide through by delta x. So if each one of these terms gets divided by that delta x, that leaves us with 3x squared plus 3x delta x plus delta x squared. And now we go ahead and let delta x approach 0. So we get 3x squared plus this is going to 0 plus this is going to 0. The limit is 3x squared. So we've proved that the derivative of x cubed is 3x squared. Now what about x to higher powers? X to the fourth, x to the fifth, x to the sixth, x to any positive integer power. Well, notice the pattern with what happens when you take x plus delta x and you raise it to some whole number power. X plus delta x to the fourth is x to the fourth plus 4x to the third delta x plus 6x squared delta x squared plus 4x delta x cubed plus delta x to the fourth. X plus delta x to the fifth is x to the fifth plus 5x to the fourth delta x plus, and so on. And in general, there is something called the binomial theorem that tells you in general what you get when you take a binomial, something plus something else, to some whole number power and you multiply it out. But for our purposes, the part we really need to know is that what you get when you multiply out x plus delta x to some power is the first term is always x to that power, and the second term is always that power times x to that power minus 1 times delta x just to the first power, and then all the rest of the terms involve delta x to the power 2 or more. Notice how the terms involve x to the fifth power, fourth power, third power, second power, first power, and 0th power. And the terms involve delta x to the 0 power, 1 power, 2 power, 3 power, 4 power, 5 power. And then the coefficients are 1 and 5, and then some others that, for what we're doing right now, we don't really care about. This is what we need for this proof. That if you take x plus delta x to the nth power and multiply it out, you get x to the n plus n times x to the n minus 1 times delta x, plus other terms that each involve delta x to the power 2 or more. So if we subtract x to the n from that, we're subtracting off that x to the n that comes at the beginning, So what's left is n times x to the n minus 1 times delta x, plus the other terms that involve delta x to the power 2 or more. Then if we divide everything through by delta x, that first term no longer involves delta x. It's just n times x to the n minus 1, but all the other terms still involve delta x to at least the first power. So now, when we take the limit as delta x approaches 0, that first term isn't going anywhere, but all the other terms are going to 0, so the limit we get is n times x to the n minus 1, and so that is the derivative. So that proves that the power rule works when the power, the n that you're raising x to, is a positive integer. What about if n is a negative integer, or a fraction, or an irrational number? Well, in that case, it's a lot harder to prove without using some other rules that we haven't gotten to yet. So for now, I'm not going to worry about the proof of the power rule in general. It's possible to prove it, but not, or at least not easily, without some other rules that we haven't gotten to yet. Now, as far as giving you an informal or intuitive explanation of why it works, why the rule is the way it is, I don't know how to do that in general, but I can at least offer, for what it's worth, think of the function x cubed. And if you want to visualize what this function is doing, think of an actual cube that is x units long on each side. So x cubed is the size or the volume of that cube. And think about how that changes if x changes. If you let x, the length of each side or edge, increase by a little bit, what happens to the size of the overall cube, the value of the function x cubed? Well, it's growing in each of 3 dimensions or directions. And the amount that it grows by kind of depends on how big that face of the cube is. But that face of the cube has an area of x squared, x by x. So it kind of makes sense, or at least I think it makes sense, that the overall size or volume of the cube would grow at a rate that's proportional to 3 times x squared. Now, if you had x to a higher power than 3, then to visualize what's going on, you'd have to think in more than 3 dimensions, which is pretty much impossible to actually visualize. And as for other powers that aren't even whole numbers, well, I don't know of a good way to visualize that or to explain why it makes sense. If you know of a way, let me know. But otherwise, you'll just have to sort of accept that the rule works. Okay, next rule, the constant multiple rule. If c is any real number, the derivative with respect to x of c times f of x is c times f prime of x. In other words, the derivative of a constant times a function is the constant times the derivative of the function. Now, don't confuse this rule with just the plain old constant rule that we saw earlier. The derivative of a constant by itself would be 0. But the derivative of a constant times something else would be that same constant times the derivative of the something else. How would you prove this? Well, it's pretty straightforward if you just use that, if you just refer to the definition. According to that definition, the derivative of c times f of x should be c times f of x plus delta x minus c times f of x over delta x, and then the limit of that as delta x approaches 0. The other side of this equation is c times f prime of x, c times the derivative of f of x. And that should be c times what the definition says the derivative of f of x is. So to prove that this rule works, we just have to show that these two expressions are equal to one another, that they are equivalent. And that's not too difficult. Just have to do a little algebraic manipulation. If we start with this, we can factor out the common factor of c in the numerator, right? That is c times the quantity f of x plus delta x minus f of x. And if c is a factor of the numerator, we can think of it as a factor of just the whole fraction. C times the whole fractional expression f of x plus delta x minus f of x over delta x. And then we know, well, if you remember the limit laws that I showed you in my video about limits, the limit of a constant times a function is the constant times the limit of the function. But that just is, by definition, c times the derivative of f of x. That is c times f prime of x. So that completes the proof. So in this case, at least, the proof is just a straightforward matter of showing that what the definition says this is and what the definition says this is are equivalent. Why does this make sense? Well, again, if you think of derivatives as rates of change, and you take a function and you multiply it through by a constant, like for example 3 times f of x would be 3 times the size of f of x itself. So any change in the original function f of x should correspond to a threefold change in 3f of x. So however big x is and however big f of x is, 3 times f of x should change by an amount that is 3 times as much as what f of x is changing by. And as with all of these, if this helps you visualize or make sense of why the rule works, great. And if it doesn't help you, you can just ignore it. On to some examples. Suppose f of x is 10 times x cubed. So here we have a constant times a function. So the rule says the derivative of a constant times a function should be the constant times the derivative of the function. Here the constant is 10, and the function was x cubed, so the derivative we know is 3x squared. So the overall derivative of 10x cubed is 10 times 3x squared, or 30x squared. And pretty soon you get the hang of these and you jump directly from 10x cubed to 30x squared. You say right away, oh, okay, we got 10 times 3, that's 30, times x to the 3 minus 1 power. Suppose f of x is x squared over 11. And another way to write that would be as the number 1 over 11 times x squared. If we think of it as x squared over 11, it doesn't really fit any of the rules that we've seen so far. But if we think of it as the number 1 over 11 times x squared, then it is a constant times a function, and it does fit the rule that we have. The derivative of 1/11 times x squared would be 1/11 times the derivative of x squared, which is 2 times x to the first power. And I can go ahead and multiply together 1/11 times 2 and write that as 2/11. So the derivative is 2/11 times x, or 2x over 11. What about if f of x is 22x? That's a constant times an x, so the derivative should be the constant times the derivative of x. And remember, the derivative of x is 1, so we get 22 times 1, or just 22 for our derivative. What about if f of x is 8 over x cubed? The way it's written now, it's not exactly in the form a constant times a function, but we can rewrite it just a little so that it does look like that. So it looks like 8 times 1 over x cubed, or 8 times x to the negative 3 power. And now we do know how to find the derivative of that based on the rules that we've seen. The derivative would be the constant 8 times the derivative of x to the negative 3, which would be negative 3 times x to the negative 4. And so that would simplify to negative 24 x to the negative 4, or negative 24 over x to the 4th power. And what about if f of x is 6 times the square root of x? We've already seen how to find the derivative of the square root of x. We can think of it as x to the 1/2 power and use the power rule on it. So the derivative of 6 times x to the 1/2 should be 6 times 1/2 x to the negative 1/2. And since 6 times 1/2 is 3, I can write this as 3 times x to the negative 1/2, or as 3 over x to the 1/2, or as 3 over the square root of x, all equivalent. Finally, and this is a 2-for-1, 2 rules for the price of 1, the sum and difference rules. The derivative of a sum is the sum of the derivatives, and the derivative of a difference is the difference of the derivatives. In other words, if f and g are any two functions, or I should probably specify any two differentiable functions, because we are assuming that f and g individually do have derivatives. If f and g are any two differentiable functions, then f plus g is differentiable, and its derivative is just the derivative of f plus the derivative of g. Likewise, the derivative of f minus g would be the derivative of f minus the derivative of g. Why is this true? Well, this is pretty easy to prove. Again, it's a matter of showing that what the definition says that the left side of this equation should be, and what the definition says that the right side of this equation should be, match up. So according to this definition of a derivative of a function, the derivative of the function f of x plus g of x should be, well, you take that function, but with x replaced by x plus delta x. Then you subtract that function just itself, just in terms of x, put it all over delta x, and then take the limit as delta x approaches 0. Meanwhile, what the definition says that f prime of x should plus g prime of x should be is, well, here's the derivative of f of x. Here's what f prime of x should be. And here's what g prime of x should be. It should be the limit as delta x approaches 0 of g of x plus delta x minus g of x all over delta x. And we just have to show that these two expressions are equivalent, that one can be manipulated into the other. So to do that, let me start with this, and first let me get the brackets out of the way and distribute the minus sign. So we got f of x plus delta x plus g of x plus delta x minus f of x minus g of x. And let me rearrange the terms in the numerator so that the f parts are together and the g parts are together. So it's f of x plus delta x minus f of x plus g of x plus delta x minus g of x. And now I can separate this into two separate fractions that each have that same denominator. So we got f of x plus delta x minus f of x over delta x, plus we got g of x plus delta x minus g of x all over delta x. And then the limit of a sum is equal to the sum of the limits. So that's equal to the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x, plus the limit as delta x approaches 0 of g of x plus delta x minus g of x over delta x, which is, by definition, f prime of x plus g prime of x. So that completes the proof. Now that was for the sum. What about for the difference? What about for the rule that says the derivative of f minus g is the derivative of f minus the derivative of g? Well, one way to prove that would be pretty much the same thing we just did, only with minuses here and here instead of pluses. Just do it directly from the definition. I'm not going to show you all the details, but it works out pretty much like what we just saw when we were doing the sum. Way number 2 would be to think of f of x minus g of x as f of x plus the constant -1 times g of x. And then we've already proven the rule that says the derivative of the sum is the sum of the derivatives, and we've already proved that the derivative of a constant times a function is the constant times the derivative of the function. So that should be enough to prove that the derivative of f of x minus g of x is the derivative of f of x minus the derivative of g of x. And I guess I didn't specify an intuitive reason why this works, but if you've got two things added together and they're both changing, how fast is the sum changing? Well, it depends on how fast the two individual things are changing. If some amount gets, if each individual part grows by a certain amount, then the whole thing is growing by an amount that's equivalent to how much the first thing grew by plus how much the second thing grew by. But now let's look at some examples. If f of x is x squared plus 1, the derivative should be the derivative of x squared, which is 2x, or 2x to the first power, plus the derivative of 1, which would be 0. So that, of course, simplifies to just 2x. If f of x is x squared plus 1, f prime of x is 2x. If f of x is x to the fifth minus 3x, the derivative should be, well, it should be the derivative of x to the fifth minus the derivative of 3x. And we have rules that show us what those derivatives should be. They should be 5 times x to the fourth minus 3. The derivative of x to the 5 power is 5 times x to the 4 power. And the derivative of a constant times a function is the constant times the derivative of the function, and the derivative of x is 1. What about if f of x is x to the fourth plus 5x to the third minus 2x squared plus 7x minus 13? Well, we can just differentiate this term by term. We can say, well, the derivative of that whole thing should be the derivative of x to the fourth, which is 4x to the third, plus the derivative of 5x to the third, which would be 5 times 3, or 15, times x to the 2 power, minus the derivative of 2x squared, which would be 2 times x to the 1, so 4x, plus the derivative of 7x would be 7, because it's 7 times the derivative of x, minus the derivative of 13 is 0, because the derivative of a constant is 0. Notice that using the rules that we have, we can now find the derivative of any polynomial. This was a polynomial, and it was relatively easy to differentiate term by term using the rules that we have here. So we now have enough rules that allow us to find the derivative of any polynomial function, as well as some functions that are not polynomials. There are other functions that we don't yet know how to find derivatives of using these rules. They don't apply to every function you might ever want. There are more rules to come, but the rules we have now take care of a pretty good chunk of the functions that you might want to find derivatives of. So suppose we want to find the slope of the tangent line to the graph of the function f of x equals x squared minus 4x plus 3 at the point 5, 8. Now, since the derivative does give us the slope of the tangent line, this amounts to finding the derivative of this function at the point where x is 5. Now, this is an example that I already did in the previous video, working directly from the definition, that limit definition of what the derivative is. But now we can solve this a whole lot easier just by using the rules to find the derivative. We can almost immediately say, oh, f prime of x should be 2x minus 4. It'd be the derivative of x squared, which is 2x, minus the derivative of 4x, which is 4, plus the derivative of a constant is 0. And then we just go ahead and plug in 5 for x, and we get 2 times 5 minus 4 is 10 minus 4, or 6. So the slope of that tangent line, 6. Okay, one more example. What if we want to find the derivative of the function f of x equals x to the fifth minus 5x plus 20 over x? Now, your first thought might be to take the derivative of the numerator over the derivative of the denominator. But we do not have a rule that says we can do that. In fact, there is no such rule because when you have something over something else, the derivative of the whole fractional expression is not just the derivative of the numerator over the derivative of the denominator. There is a rule that tells you what you do get for the derivative, but it's more complicated than just taking the derivative of what's on top over the derivative of what's on the bottom. So that quotient rule is coming up in a later video. I'm not going to show it to you now because for this function, we don't really need it. We can rewrite this function. We can split it up into x to the fifth over x minus 5x over x plus 20 over x. And then that simplifies to x to the fourth. X to the fifth divided by x is x to the fourth, minus 5. 5x divided by x is 5, plus, and instead of writing it as 20 over x, I can write it as 20 times x to the negative 1 power. Now, so far, this is still equal to the function I started with. This is still just another way of writing f of x. But now I'm ready to take the derivative. The next line is going to be f prime of x. So f of x equals this, which equals this, which equals this. So f prime of x, the derivative of that function, would be 4x to the third minus 0, because the derivative of a constant is 0, plus, now for the derivative of 20 times x to the negative 1, we get 20 times negative 1 times x to the negative 1 minus 1. So that's why it's a minus 20 times x to the minus 2. Or we could also write this as 4x cubed minus 20 over x to the 2 power. So there's the derivative. Now, that's where I'm going to stop with this video. But there are, as I said, more rules that we haven't gotten to yet that you might need to find derivatives of other more complicated functions. So those other rules that we haven't gotten to yet include something called the product rule for when you want to find the derivative of a function that consists of one thing times another thing. There's the quotient rule for when you want to find the derivative of a quotient, a function that consists of something over something else. There's something called the chain rule that has to do with composite functions, like a function of another function. And then there are rules for finding the derivatives of the trigonometric functions like sine and cosine and tangent, and their inverses like arcsine and arctangent, and for the derivatives of exponential functions like e to the x, and logarithmic functions like ln of x. So that's not covered in this video, but I'm hoping to follow it up with some more videos where I do explain those other rules. So thanks for watching. Hope this was helpful. See you later.